Okay, welcome to lesson 3 of chapter 5 Radians from year 2 pure maths. Today we're going to look at how to solve trig equations, but in radians this time. So this is going to be a really good revision of the work you did last year, in particular trig identities and equations chapter 10. All right, now this is complex, but there is a clear methodology behind it. Okay, and you're also going to need to be familiar with these two identities here. These need to be learnt, okay, but I've given them to you for today's lesson. Okay, and these are the only two trig identities that you've been given so far. There's going to be more to come this year. Okay, now please pause the video and have a go at the 4 warm-up questions. Okay, and let's have a look at the solutions. Now, for question 1, you may have noticed this is the first part of a rather longer question. So questions 1, 2, and 3 would form a full question for solving a trig equation from last year. Now, the reason I've done this is because while we're revising this, I want to break it down into some smaller steps and we can talk about them in some detail. So in question 1, we're given the equation cos of 2 theta equals a half. And then we're given this substitution to make here. So given that x equals 2 theta, we're asked to find the principal angle for x. Okay, we'll talk about the principal angle in a second. The first thing to do is to substitute the x for 2 theta. I should have said that the other way around, the 2 theta for x. So in other words, cos, and instead of 2 theta, we're going to put x in, is equal to 1/2. Okay. Now, the reason we do this is because we're going to be dealing with x throughout most of this method, and it makes the method a lot more straightforward. Okay, and then we're going to bring the 2 theta back at the end. Okay, now this brings us on to the principal angle. Now, what is the principal angle? Well, I'll put it in bold there because it's quite important. The principal angle is the angle you get when you find the inverse cosine of a half, which would be the next step in this equation. All right, so let's do that. So if we find x is just simply going to be the inverse cosine of a half. And you may or may not know this, but if you do that on your calculator, and this is going to be in degrees, this is 60 degrees. So it's a nice answer. All right. Now, why is this called the principal angle? Well, when you do the inverse cosine of a half on your calculator will always give you an acute answer. Okay, always. But we know from experience that the cosine graph crosses the x-axis many, many times. In fact, an infinite number of times if we allow for a domain of x for all real numbers. So we have to limit the interval in which we're looking in order to reduce the number of answers. So you'll only get an answer. Okay, I'm going to make a note of this because it's really important. The principal angle. So on your calculator, it's the acute angle. Answer. Okay, it's just a very crude way of saying it. So it's the acute angle answer. All right. So you'll always get an acute answer, and that's called your principal angle here. So 60 is our principal angle. Okay. And we give our answer in degrees. I hope that's okay. So it's just using this substitution here. First of all, that removes the 2 theta, and then we've got an acute angle for 60 degrees. And then next up, we're going to find how many other solutions there are going to be to this equation. Okay, so moving on to question 2. It says following on from question 1, which is good. So that's the first bit done. We're going to adjust this interval that we've been given here. So this interval is from 0 to 360. And like I was just saying, we know that the solution to the equation that we were given in the question, this equation here, has infinite solutions if we allow for all values of theta. okay, for all real values of theta. So we limit ourselves to just looking in this interval, okay? Now then, because we've said that x is equal to 2 theta, okay, we're going to write an interval now for x because it's the big X that we're going to be doing our calculation with. So let's write out our interval. So we've got 0 degrees is less than or equal to theta, which is less than or equal to 360. So our final answer theta is going to be values between 0 and 360 inclusive. Now, how do we get 2 theta? Well, let's double the entire interval, okay, because we've got x equals 2 theta. So when we do that, we're going to get 0, because 2 lots of 0 is just 0, 2 theta, and if you double 360, you get 720 degrees. Okay, so that's good. Now, we know as well that 2 theta has another name. Okay, we've called it x, haven't we? X is 2 theta here. So we can now write our final interval as this. So this means we're going to be looking for solutions between 0 and 720 when we're talking about x. And we have a principal angle ready to go, this 60 degrees over here. So now in question 3, let's put these ideas of the principal angle and the adjusted interval together in a full question. So you'll notice straight away you've got an interval defined between 0 and 360. We may need to adjust that. We've got the 2 theta there, which we can replace with x in a moment. So let's just rearrange this and make cos of 2 theta the subject. So we're going to make cos 2 theta the subject. Now, I'm sure you managed to do this without too many problems. So if I'm just going to write this down, it's going to be cos 2 theta is going to be equal to, well, 4 subtract 3 is 1, and then divide by 2. So it's going to be a half, which we met in question 1. So we've got the same equation. Okay, I've just basically added another step, which is a bit more realistic, like what you would get. We've then got our principal angle, haven't we? So we can now say, let big X equal 2 theta. Okay, so therefore, cos of, and we'll place that 2 theta with big X, all right, is going to equal 1/2, like that. And now we can get our principal angle. Let's do that now. So principal angle. So therefore, X is going to be the inverse cos of 1/2, which equals 60 degrees. We've already done this. And this answer that your calculator spits out at you, okay, even though there's other answers, such as 300, okay, that would also give you a half if you did the cosine of that. This is called the principal angle. Okay, and it's always acute. Now, why is it always acute? Because when you calculate the principal angle, what you've got to make sure is that if this number here is negative, you just ignore the negative sign when you put it into the calculator. So that needs to be made positive. Okay, so we've got our principal angle now. We adjusted our interval for X in question 2. So let's make a note of our adjusted interval. So this was adjusted to all angles between 0 and 720. Okay? Which makes sense. All right. So if I just draw your attention to the 2 equations, we've just rewritten the equation as cos of x equals a half. We're going to solve that instead of cos 2 theta equals a half. And we're going to look in the interval 0 to 720 rather than between 0 and 360, okay, which was for this question. Okay, so it just makes more sense. Now we're going to use the cast diagram now to find all our solutions. So I'm going to draw the cast diagram here. Hopefully you should have enough room for this. All right, and we're going to label it C, A, S, and T. And then you put your principal angle on the cast diagram. Okay, your principal angle is acute. It's always acute, so it goes here. Okay, why does it go there? Well, because again, that value was positive. Okay, sorry, this value here is positive. Okay, and the cosine of an angle which gives a positive answer must be in the first quadrant A and the fourth quadrant C. So we're going to put another 60 degrees in the fourth quadrant. So these are the only two quadrants that will give you positive values of cosine. Okay, so we put it in the two quadrants. When you're using the cast diagram, unless you're trying to solve two questions in one, you're always going to put two angles. For example, if the question was cos x equals negative a half, your principal angle would still be 60 degrees because you would ignore that negative. And when you're calculating the principal angle, you would still do the inverse cos of a half. You would just drop that negative. Okay. Then, rather than putting the 60 degrees in A and C, which are here, if the cosine of x was equal to negative a half, you would simply put the 60 degrees in S and T, which is where cosine is negative. All right, but that would be in a different question. So I hope that makes sense. Okay, now we've got the cast diagram, we can now find all our x values. So what do we have? Well, we've got big X would be equal to, and we start at 0, of course. 0 is here. Okay, and we go anti-clockwise in the positive direction around the cast diagram. All right, let's do this. So we've got 60 degrees. That's our first answer, the principal angle. Then we get all the way round to 360, but we have 60 less. So our next answer is going to be 300 degrees. Okay, and remember, we have to look between 0 and 720. So we've got to go around again. So we go around again. We start at now we're at 360 here. Okay, and we go around again. So this is going to give us an angle of 420 degrees. And the final angle is going to be 60 degrees less than 720, which is, of course, 660 degrees. So we've got 4 answers, which is what you would expect. For a normal trig equation, you would expect 2 answers. If it was just like cos theta equals a half, there would be 2 answers. If it's cos of 2 theta equals a half, then there's 4 answers. The number of answers should double. All right, now we know that this is the values for x. Now we need to solve this equation in terms of theta. So now we can go back to our theta, and we know that all these values here are equal to 2 theta. Okay, 2 theta is equal to all of these. Okay, so we just have to divide by 2 to get our values of theta. So therefore, theta is going to be 30 degrees, half of 300, which is 150 degrees, 210 degrees, and 330 degrees. Okay, and that's question 3 done. Now for question 4, we have to find the exact value. So it's stipulating there's only one value here. Okay, and we can see that that's going to be the case because we have a domain defined for theta, which is just between 0 and pi over 2. So it's just going to be the acute answer, nothing else. So what do we do here? Well, we're in a bit of trouble, really. We've got cos of theta here, and we've got sine squared here. So we have what I would call a linear term and a squared term. So it looks like this is some sort of quadratic. Okay, that's what you should be thinking. If you see a squared term and a linear term, then maybe this is a quadratic. Now, how do we solve this? Well, you'll notice here that this is cos theta. Now, we're going to get, because that's the linear term, we're going to get everything in terms of cosine, okay? So we want this sine squared over here to be a cos squared theta somehow, okay? Then we've got a cos squared and a cos, and we can solve the quadratic. So how do we do that? Well, we use the identity. So we're going to use the fact that sine squared theta plus cos squared theta is absolutely identical to 1. And if we rearrange it, we know that sine squared theta is exactly the same as 1 subtract cos squared theta. Okay? And this is going to be substituted into our equation. Let's do it. So let's rewrite the equation, and we're going to replace sine squared with 1 subtract cos squared. So 5 subtract 7 cos theta is equal to 2. I'm going to open a bracket, multiply by 1 subtract cos squared theta, and then I'm going to close the bracket. Okay, that will get you method marks on the exam. Let's simplify, rearrange, collect like terms. Okay, so we'll expand the bracket first. So 5 subtract 7 cos theta is equal to 2 subtract 2 cos squared theta. Okay, let's get the cos squareds on the left by adding 2 cos squared theta to both sides. Okay, then I can subtract the 7 cos theta. And then if I subtract 2 from both sides, that's going to give me plus 3 equals 0. We now have a quadratic equation we can solve. Now, you could solve this directly if you want to. You can use a calculator, put in the coefficients A, B, and C. Okay, whatever you want to do. I'm going to try and factorize this. Okay, and also if you're not comfortable with the cos theta that's in the equation, you can use a substitution. So that's up to you. You could say I won't use big X again. Let's call it big Y. Let big Y equal cos theta. Okay, now if you do that, your equation is going to look like this. So therefore you would get 2 big Y squared subtract 7 big Y plus 3 is equal to 0. Okay, let's factorize this. So we're going to have 2y. Let me just have a look at the factors here. Okay, so I want -7, so I'm going to need -3 there and -1 there to create the plus 3. So my solutions are going to be y is equal to 1/2 or y is equal to 3. Notice as well, we're going back to solving quadratics. This is never going to go away. Let's put the cos theta back in. So cos theta is equal to 1/2 or put it back in as well. So cos theta is equal to 3. Okay, lots of skills on showing these questions. Now then, notice this question could have gone in this direction. It could have gone back to question 3, and we could have solved it in a wider interval between 0 and 360. Now, we don't have to do that simply because we only want the acute answer. Now, if we do the inverse cos of 1/2, we're going to get the theta value of 60 degrees again. Okay, here. And that's the only answer because of this domain. Okay, we don't have to worry about any of the others. Now, I know it's in radians. We're going to convert it in a second. Okay, I know it's, so that's 60 degrees. And the answer over here, cos theta equals 3. Well, we know, hopefully, that cos theta is bounded between -1 and 1. If you draw the cosine graph, the graph is never greater than 1 and it's never less than -1. So this cannot happen. This has no real solutions whatsoever. It has complex solutions, but that's for further mathematicians. So the question is, we just need to give the answer in radians, okay? And we know the answer is in radians because it's specified between 0 and pi/2, which is 90 degrees. So just to finish off, I'm just going to go up here because I'm running out of space. How do we get that into radians? Well, if you'll recall, we know that pi radians is equal to 180 degrees. Okay, so if I divide both sides by 180, that gives me 1 degree. So I simply have to multiply both sides by 60. Okay. Now, this is the long way of doing it, but it's the fail-safe way of doing it, okay? And 60 over 180 is obviously 1/3, so that's going to be pi/3. You'll probably notice, though, that 60 degrees, if just work it out as a fraction of 180. What is 60 as a fraction of 180? Well, it's 1/3, isn't it? And remember that you can interchange 180 and pi when you're converting between degrees and radians. So just work out what is the fraction of 60 out of 180, and that's the fraction of pi that you have. So in other words, pi/3. So this is your final answer here, pi/3 radians, and we're done. Okay, so for this lesson, we're going to look at 2 worked examples, and simply it's going to be solving trig equations using radians instead. Now, I'm going to cheat a bit here. I want you guys to feel comfortable doing this, and I think this is a good opportunity to go over those skills that you met last year. So you'll notice that this implies that this interval is in radians. Now, what I'm going to do is I'm going to rewrite the question, but we're going to do it in degrees instead. And if we go through the steps in degrees and then switch our answers to radians at the end, that will be totally sufficient, okay? The problem is with this, or the drawback, is that although we're not dealing with radians throughout the question, you have to remember to convert back from degrees to radians at the end. Okay, so we'll put some strategies. We'll put some strategies in place to deal with this. So I'm going to rearrange the equation first of all. So if you notice, we've got 2 sine 3 theta equals √3. So this means that sine of 3 theta is equal to √3 divided by 2. Okay, and we're going to do this in the interval 0, okay, up to 360 degrees. Now, this is where we have to err on the side of caution. Right, now, suppose you're doing this in an exam. You could do all the work, it's all perfect, and then you get to the last step and you don't give any of the correct answers because you've done it in degrees rather than radians. So let's make it absolutely clear to ourselves so that we don't forget that this is a radians question. Just write it in big letters so you don't forget, okay? This would be my advice to you guys. Okay. Now, let's just proceed as normal so we can use the skills we've just met earlier in the warm-up. So we have sine of 3 theta. Now, we're going to use a principal angle here. So I'm going to say, let big X equal 3 theta. And also, there's a couple of other things we can do here. We can make some predictions. And it's a good idea to do this because you'll have an idea in your head whether you've done this correctly. The fact that we're dealing with 3 theta here, okay, well, remember, if we're solving a trig equation which is just sine theta, for example, we're going to get 2 answers at the end, okay, unless there's some kind of peculiarity in the question. If you do a question with sine of 2 theta, the number of answers doubles, so that would be 4 solutions. Now, in this case, we've got 3 theta, so we can expect 6 solutions. Okay? All right, that's what we're thinking. I hope that's clear. So we're expecting 6 solutions, and we also need to remember those 6 solutions are going to be in radians. All right, so just have one eye on that, and don't forget about the radians as well. Right, okay, so let's make the substitution. So we now know that sine of what's going to be big X is equal to root 3 over 2. We know this is a nice value, so we're not going to be dealing with decimals here, which is good. Okay, and the root 3 over 2 is a positive. Let me just undo that. It's a positive value. Okay, it's a positive value. That means I don't have to take away the negative sign when I'm doing the principal angle. Okay, that's really important. So let's find the principal angle now. So I can just do the inverse sine. So the principal angle X is equal to the inverse sine of root 3 over 2. If you do that on your calculator, all in degrees, of course, you're going to get 60. Again, why not? It's nice and straightforward. Okay, when we're making, it's about the methodology, isn't it? It's not about having complicated answers. All right, so there's that. Now, we've got our principal angle. What was question 2 all about? Well, we had to adjust our interval. So let's adjust the interval here. Adjust the interval. Okay, so the interval states, we're going to use this modified interval over here. Remember, I'm not going to be using the radians, not yet anyway. So the adjusted interval, so we're looking between 0 and, let me just undo that, looks a mess. No, this interval here. Okay, and I should have put degrees on there as well. So the adjusted interval is going to be from 0 degrees. Okay. Well, let's just write it out again first. So from 0 up to 360 degrees, we want 3 theta. Okay, 3 theta. We're going to need to multiply this by 3, this interval. Okay, so if we do that, we're going to get 0, 3 theta. And then if we do 360 multiplied by 3, that is 1080 degrees. So in other words, just as a note to yourself, so it's the cast diagram. We have to go around 3 times. Right, because of this, again, because of this 3 theta. That's the other implication. So the other implication being that you're going to have 6 solutions, most likely, and you go around the cast diagram 3 times. Great. Now let's move on to the cast diagram. So I'll do the cast diagram up in the top right, since I've got a bit of space up here. So cast, so C, A, S, and T. Let's add our principal angle. And remember, we know that this angle is positive. Well, sorry, not this angle. This value here is positive. So that's going to go in the positive part of the cast diagram for sine. So where is sine positive? Well, sine is positive in all and in S, or sine, I should say. So we're going to put the 60 degrees here and here. All right. Okay. Great. Now let's go around the cast diagram. So we're now going to write down our solutions. These are going to be in degrees, and they're going to be for x, not for what we want. So my solutions for x, if I go around 3 times, well, my first angle, if I start at 0 and work anti-clockwise, my first answer is going to be my principal angle 60 degrees. Okay. The next one is going to be 60 less than 180. Okay, so that's going to be 120 degrees. Just in case you're not sure why that is. Okay, this is 180 here, and then we have to go 60 less to get to this blue line. All right, so that's going to give us the first 2 solutions. Now, quick way of doing this is if you're going around 2 more times, then we just add 360 to these 2 values. Okay, so if I add 360 to 60, my next one, without doing any work really, is just going to be 420. Okay, and then if I add 360 to 120, that's going to give me 480. Okay, so once you've got the first 2, it's easy. You're just adding 360 to get the next set. Okay, and then obviously to get the next pair, you're going to add 360 degrees again. Okay, so 360 to 420, well, that's going to give us 780 degrees. And lastly, we're going to have 360 added to 480, so that's going to be 840 degrees. Right, and we have 6 solutions as predicted. So this is good. Okay, now these are the solutions for x. Now there's 2 problems here. X is equal to 3 theta. Remember, x is equal to 3 theta. That's how we defined it earlier. So we're going to have to divide all of these numbers by 3 in order to get our value of theta in degrees. So this means that theta is going to equal 1/3 of all these answers. So we're going to have 20 degrees. Okay, 40. 140 and 160. All right. 260 and 280. Okay. Double check these. Don't make a mistake at this stage because you've done all the hard work now. All right. And now to get our angles in radians, remember that radians is staring at you. Do not forget about it. It's there. Your answer needs to be in radians. What we're going to do? Well, to convert to radians, this is the quick way of doing it, which I'll show you now. Remember that pi radians is equal to 180 degrees, which means that 1 degree is equal to 180 over pi. All right. Now that's fine. So this means that we just have to, sorry, I said that wrong. Apologies. Pi radians is equal to 180 degrees. That means that 1 degree is equal to pi over 180. Radians. All right. So all we have to do is multiply all these angles by pi over 180. So therefore, theta is going to be 20 pi over 180. You just literally insert pi over 180 into the answer. Okay, and then drop the degree symbol because these aren't degrees anymore. 40 pi over 180. 140 pi over 180. Keep going. 160 pi over 180. 260 pi over 180. You probably want to fast forward this bit. And 280 pi over 180. Okay, so if you're converting from degrees to radians, this is the sort of quick way of doing it. You see, you just got the pi over 180 multiplying every single one of these. Now, there's nothing wrong with the answer except they probably need to be simplified. So just to finish off, and I know I've drawn this out, but I really need to get these points across. They're really important. So if you can simplify them, this is going to be pi over 9, 2 pi over 9. It's just double the previous one. 7 pi over 9. 8 pi over 9. 13 pi over 9. And the last answer would be 14 pi over 9. If you do have time on your exam, you can check whether these are correct, and you could walk away with some certainty about whether you've done it right or not. Because we anticipated 6 solutions, that's the right idea. We've got the 6 solutions, and if those 6 solutions satisfy the equation we were given initially here, then they must be correct. Okay, so that's worked example 1 done. Okay, so for our final example, example 2, we're asked to solve what looks like a quadratic trig equation in this interval 0 to 2 pi. Now, once again, what we can do is, if we are more comfortable, we can do the whole question in degrees and then convert it to radians at the end. Okay, and that way we can reinforce those skills we learned last year. So once again, let's rewrite the question. So we're actually going to solve 3 sine squared theta plus 13 cos theta plus 7 equal to 0. And we're going to change the interval from radians to degrees. And hopefully now you know that 2 pi radians is, of course, 360 degrees. So just basically swap these numbers. Okay, and then obviously 0 radians and 0 degrees are the same. Okay, let me just put the degree symbol on there as well. Now, before we proceed, we've got to make sure that we don't forget to convert back into radians at the end. So what you can do, just write radians in big letters like that so we don't forget. All right, it may be an exam situation and we want to get the right answers. Okay, so let's go back to this. So we'll do it in degrees and then convert at the end. We have a quadratic. Now, we look at the linear term, what I call the linear term here, and there is a cos theta. What that is telling you is that this needs to be a quadratic in terms of cos theta. Okay, so we need a quadratic in terms of cos theta. That's what that's telling you. All right. It's not going to be in terms of sine theta. Okay. You always use the linear term as the guide. Okay. The linear term tells you what trig ratio to convert it into. Now, this means that we have to do something about the sine squared theta here. Well, we can do that. We can use the identity that we were given at the start of the lesson that you need to remember. We need to remember that sine squared theta plus cos squared theta is identical to 1. Okay? And let's make sine squared theta the subject. So therefore, sine squared theta is identical to 1 subtract cos squared theta. We can now make a straight substitution now for the sine squared and this. Okay, and this will get you your first method mark. So let's rewrite the equation. So we're going to have 3 open bracket, and I'll write it in red so we can see the substitution. 1 subtract cos squared theta, close the bracket. Okay, and then everything else remains the same. So we're going to add 13 cos theta plus 7 is equal to 0. Okay, now we need to expand, simplify, collect like terms. So therefore, 3 subtract 3 cos squared theta, add 13 cos theta, add 7 is equal to 0. Now, I think I'm going to add 3 cos squared theta to both sides, subtract the 13 cos theta, and then subtract 10. So this is going to give me 3 cos squared theta. Okay, adding the 3 cos squared theta. I'm going to subtract the 13 cos theta, and I'm going to subtract 10, which will give me 0. Okay, that's just collecting like terms. Okay, now depending on how comfortable you are with this, we've got a quadratic we can now solve. So if you prefer, we can now say, let's say I won't use big X because that will confuse us with the principal angle. Let's say let big Y equals cos theta, like that. Okay, so now we can say, all right, 3y squared subtract 13y subtract 10 is equal to 0. Okay, now we can try and factorize this. So we're going to have 3y. Okay, let's see what the factors are going to be. We've got y over here equals 0. Now I need to create a minus 13. So if I put a minus 5 there, that'll be minus 15. And then if I add the 2, that should do it. Okay, you can use whatever strategy you like for factorizing, or you can just put the A, B, and C into your calculator. So our solutions are going to be y is equal to negative 2 over 3, or y is equal to 5. Putting the cos theta back in, this tells us that cos theta is equal to negative 2 over 3, or cos theta is equal to 5. Now, once again, we know, I've stressed this in the previous example, the range of cosine stretches only between -1 and 1. So this is outside the range, so we can discount this one completely. So this is going to be the equation we're going to solve. We've eliminated all the complexity out of the quadratic now, and we've boiled it down to a single linear trig equation that we need to find the solutions for. Okay, so we've got the equation and we've got the interval up here. So we're going to solve this equation. All right, so let's do that on the other side of the page. So we're now asked to solve cos theta equals negative 2 over 3 okay, in the interval 0 up to and including 360 degrees. I've still got my eye on that radians above, so I know I'm going to be converting later. All right, now let's just do a couple of predictions here. What can we expect to get? Well, we've only got one theta, okay? So that means there's probably going to be two solutions. Which seems reasonable, doesn't it? And another way of thinking about it, we're going to do the cast diagram. Okay, so it's going to be just once. We're going to go around the cast diagram once. We also don't need to adjust the interval because we've got theta in both cases. Okay, so we can go straight to our principal angle now. No adjustment needed. Principal angle. Okay, so theta is going to equal the inverse cosine of 2 over 3. Notice that I've dropped the negative sign there. Make a note of that if you don't remember. Remove the negative sign. The cast diagram deals with the negative sign for you. Okay, so there's no negative sign on your principal angle when you're doing the inverse cos or the inverse sine or the inverse tan, whatever it is. Please remember that. You'll know it's wrong if you get an obtuse or a reflex angle or something like that. Right, so we get a nice acute angle. So this is going to be 48. I'm going to round it to 2 decimal places. That's 48.19 to dp. Now, I'm doing it to 2 decimal places because I might be rounding to 3 significant figures later. So it just makes it for the accuracy. Okay, now we can draw the cast diagram. So there's not much more to do now. Cast diagram, I'll do that here in the middle. C, A, S, and T. Right. Now remember, we've got our principal angle. Here it is. Got that. And we also know that this value is negative. And we're dealing with cosine. Right, so where is cosine negative? Well, cosine is negative here and here in S and T. So that's where we put our principal angle. So we put an angle of 48.19 degrees to the horizontal in both of those quadrants. Okay, now we can read off our answers. So theta is going to equal, we're only going around once, of course. So read off 0 anti-clockwise. What do we get? Well, we're going to get 180 subtract 48.19, which is, of course, 131.81 degrees, and 180 plus 48.19, which is 228.19. So our two angles. Remember, of course, that this point here is 180 degrees, and these are the two places where our angles live. So 48.19 less than 180 and 48.19 more than 180. So those are our two angles. Those are in degrees. Now remember, look at what you've written right at the beginning of the at the question. Right? Don't forget this. Convert back into radians. So this is going to equal, and remember, you can just multiply both of these by pi over 180. All right, that's the first one, and 228.19 pi over 180. Okay, so these are going to be our angles. Now, if you put them into your calculator, I'll let you just check this. You should get 2.30 radians for the first one and 3.98 radians for the second angle. And those are our two solutions. So we've remembered to convert it into radians. Our predictions have come true. We've got two solutions. We went around the cast diagram once. And if you have time, just plug these angles into the equation and you should hopefully get 0. All right, okay, so that concludes this lesson.